software engineers, project managers, journalists, bankers, farmers, activists, a whole gamut of different professional backgrounds, all of them looking to apply their skills to solving climate change. The Learning for Action course is an immersive exploration of climate science, climate impacts, and climate solutions. It's a combination of written classes, live weekly lab sessions, deep dives, and expert guest talks and workshops, all of which are intended to help fellows learn about climate change and also help them find their role in working to address it. Terra was founded in 2020, that was 3 years ago, with an ambitious goal of getting 100 million people working on climate change this decade. To achieve this goal, we offer a combination of climate education, connections to employers and climate jobs, and a supportive community of people who want to make a difference on climate change. You can check out our programs at Terra.do on the web, and you can download our app, which is available on the Apple App Store and on Google Play. We offer a new cohort of Learning for Action starting every 6 weeks, and we urge you to check it out if you want to learn more about how you can become involved in addressing climate change. Our next cohort begins October the 16th, so in just about 6 weeks from now. Before we get started, just a few points about this Zoom session. Please do stay on mute so we can all hear our speaker. After the talk, we should have some time for questions and answers, but we are only taking questions from our current fellows using Slido, which is an online question and answer platform. Fellows from the dingoes and elephants cohorts, you can find the Slido link for your questions on the Slack channels for your cohort. I'm now going to pass over to Cynthia. Cynthia has been an LFA instructor and now also leads our skills-based short course offerings. And Cynthia is going to introduce Kate and hand over to her. Over to you, Cynthia.
Thanks, Ashwin. Hi, everyone. Hi, elephants and dingoes. As Ashwin mentioned, I'm currently the head of learning partnerships at Terra, but previous to that, I taught a couple LFA cohorts, and I'm always super excited to see fellows again. So great to see you. And today I'm really excited to introduce your keynote speaker, who's also a good friend of mine, Kate Marvel. Kate Marvel is a senior climate scientist at Project Drawdown, the world's leading resource for climate solutions. And before joining Project Drawdown, Kate spent 7 years as a research scientist at the NASA Goddard Institute for Space Studies and Columbia University. Kate holds a Ph.D. in theoretical physics from Cambridge, and she serves on the chapter leadership team of the U.S. 5th National Climate Assessment. She's given TED Talks and testified before Congress. She was also on the Ezra Klein show yesterday, although being interviewed by David Wallace Wells. So I encourage you to have a listen to that. I'll drop a link in the chat. Kate's research centers on climate modeling to better predict how much the Earth's temperature will rise in the future. Her work has identified human influences on present-day cloud cover, rainfall patterns, and drought risk. And she's also interested in future climate changes, particularly climate feedback processes and the planet's sensitivity to increased carbon dioxide. And then really, really excitedly, Kate has a book coming out. Is it 2023, Kate? Are we still on 2023? Called Human Nature.
Fall 2024.
All right, fall of 2024 called Human Nature. So have a look out for that. But I'm really excited she's here today. You all are in for a really good treat. I don't know anyone who's better at explaining complex climate science to quote unquote normal people. So without further ado, take it away, Kate.
Thank you so much, Cynthia. I'm going to try to share my screen right now. So, all right. So I, as Cynthia mentioned, am a climate scientist. So I thought I would begin by kind of giving a grounding in what physics can teach us about the climate system, basically the science of everything. So you probably know this. This is why you are here. But for those of you who don't know, the world is warming. And global temperatures are now about 1.2 degrees Celsius hotter than they were before the Industrial Revolution. So the climate is changing. We have multiple data sets that show us this. And you know what? We understand why the climate is changing. Now, they're not as common nowadays, but there used to be a species called climate deniers. Remember those people? And often climate deniers would talk to a climate scientist and say, well, don't you guys know that climate has always changed? And we were always like, we know, we told you that. So it is true that Earth's climate has been very, very different at different points in its long 4.6 billion year old history. So, for example, the last glacial maximum, the height of the last ice age, 21,000 years ago, where I'm sitting right now in New York City would have been covered with a massive ice sheet. For those of you who are in North America or Western Europe, most of you would have been covered with an ice sheet as well. And that is because it was between 5 and 6 degrees Celsius colder during the last glacial maximum than it is now. And we know what caused this. So we know that the Earth goes around the sun, but the Earth is not an only child. We're not alone in the solar system. And the other planets and the other bodies that we share the solar system with pull on us ever so slightly. This makes our orbit change and change back again. And these changes happen really slowly over a period of thousands or even hundreds of thousands of years. So sometimes the Earth's eccentricity changes. We go from a basically perfect circle around the sun to something that's a little bit more elliptical. We also change the axial tilt. So the Earth tilts a little bit more or a little bit less on its axis. And we also precess around the axis, kind of like a spinning top. So basically that means the North Star wiggles a little bit from Polaris to Vega and back. So it's really reasonable to say, well, gravity did not end with the Ice Age. So is climate change now due to changes in the Earth's orbit? So in a climate model, we can do that counterfactual. We can ask, what would the Earth's temperature be like with only changes in the Earth's orbit? And the answer is, it pretty much wouldn't change. So whatever is causing climate change today, we can be pretty certain that it is not changes in the Earth's orbit. But could it be the sun? We know that the sun's luminosity varies over an approximately 11-year cycle as the number of sunspots change. So could it be that the sun is just getting more powerful, and that would explain why the Earth is warming up? So is it the sun? So as Cynthia mentioned, I spent years working at NASA, and I can assure you guys that if the sun was changing, somebody at NASA would probably have noticed. So we can take the observed changes in the sun's output and we can put them in a climate model, and we can see that no, it's not changes in the sun's luminosity that can explain the warming that we've experienced so far. So no, it's not the sun. But there are other things that nature can throw at us that can change the climate. So volcanic eruptions, for example. So in 1883, an enormous volcano called Krakatoa erupted. And it put so much soot and gas and dust in the atmosphere that this actually blocked the sun. And this led to widespread cooling, spreading so much ash in the atmosphere that the skies turned orange. And this time was known as a very cold time, but also a time of really spectacular, weird, beautiful sunsets. And this is something that influenced the art of the time. So Krakatoa was not the only volcano to go off. We've experienced several more recent volcanic eruptions that have had climate impacts. Most recently, Mount Pinatubo in the Philippines went off in 1991. And we know because that went off during an age where we had really good monitoring equipment, we know that the eruption of Mount Pinatubo actually cooled Earth's climate by about 0.5 degrees Celsius. So we know that volcanoes can and do change the Earth's climate. So is it volcanoes? So in a climate model, we can run that counterfactual, where the only thing that's changing is volcanic eruptions. And you can see that volcanoes have short localized cooling effects. So you can see over there, try to point here. This is Krakatoa going off. More recently, we've got El Chichon, Mount Agung, and Pinatubo in 1991. So volcanoes do change the climate, but they have really short localized effects, and these are cooling effects. They cannot explain the warming that we've experienced so far. So no, it's not volcanoes. Now, what about things that human beings have done? Well, the most visible thing that human beings have done to the Earth is change the surface of the land. So about 40% of all the land in the world that's not covered in ice is currently being used for agriculture. And that means we have cut down a lot of trees. Cutting down trees changes the surface of the earth, because when you cut down a forest, that takes something that used to be dark and absorbent and replaces it with pasture or urban area or cropland that tends to be a little shinier, a little bit more reflective. So this changes the net shininess of the earth's surface, what we scientists like to call the albedo. So is deforestation responsible for the warming? And so we can put this in a climate model. And if we account only for the effects, the changes in the Earth's albedo, the changes in shininess, we can see that land use change on these large scales actually has a very slight cooling effect. And we're certain that is because we are taking absorbent surfaces and replacing them with something more reflective. We are changing the albedo of the Earth. But deforestation, through its albedo effect, does not explain the warming that we've seen so far. So it's not deforestation that's been warming the world, but there's an asterisk here. At least it's not it's not deforestation's direct effect on the land surface. But when trees are cut down, carbon dioxide increases in the atmosphere. So deforestation emits greenhouse gases. We also know that greenhouse gases are emitted by industrial processes, making stuff. So even if you are not burning fossil fuels, the process of making cement, the process of making steel, the process of making plastic, those processes emit greenhouse gases. And of course, we know that greenhouse gases also come when we burn fossil fuels. So fossil fuel burning is the primary source of greenhouse gases in the atmosphere. But I think it's really important to stress that it's not the only human activity that produces greenhouse gases. So roughly a third of emissions total come from the combined land use and industrial processes. So human beings have done things. We have cut down forests, we've burned fossil fuels, we've made stuff, and these activities have emitted greenhouse gases. Now, if you take this history and you translate it into emissions of greenhouse gases, that becomes a story that you can tell a climate model. And the climate model tells you a story in return. It says, if you emit greenhouse gases, the world gets warmer. But if you only tell it the story of greenhouse gases, it warms a little bit too much. So what's going on? We know that greenhouse gases warm the world, but they kind of seem to over-explain the warming that we've measured. So is this because we've somehow overestimated the warming effect of greenhouse gases? Not necessarily. It is because humans have put more than just greenhouse gases into the atmosphere. And we can see some of these human activities from space, things like polluted haze or ship tracks or the smoke from wildfires. And the tiny particles, this sort of hazy smog that you can see from outer space, scientists call these particles aerosols. And aerosols have a climate effect. They affect climate directly by blocking sunlight, and they also affect climate indirectly by seeding clouds, which themselves block sunlight. So if we put only aerosol pollution in a climate model, we can see that aerosols, what we think of as pollution, this particulate matter, gas and dust that gets into the atmosphere and blocks the sun, these have a fairly pronounced cooling effect on the planet. It's not enough to cancel out the greenhouse gas-induced warming, but it's enough to mask it a little bit. So aerosols cool the world. And when you put all of these things together, you'll see that you need a more complicated story to explain the warming that we've seen so far. Humans have emitted greenhouse gases, we've emitted aerosols, we've affected the surface of the land. We've emitted aerosol pollution that blocks the sun. And together, these things pretty much completely explain the warming that we've experienced so far. So in my previous position at NASA, we collaborated with Bloomberg to develop the visualization of this data. But what I hope that you can see from here is that climate models are fueled by stories. They run on stories. Sometimes those stories are counterfactuals, like what if we didn't exist? Or what if we were doing only one thing to the climate? And sometimes the stories are true. They're the history of the world translated into emissions of greenhouse gases and aerosols. So if you tell a model a story, and that story is true, that model will tell you what really happened to the temperature. So we know that it's warming, and we know why. But what does it actually mean when the Earth heats up? Because nobody lives in the global average, and not today, because I'm in New York City and it is like 97 degrees outside right now. So I don't think global warming sounds great. But sometimes in the winter, even I think maybe a couple degrees of warming, that sounds like a pretty good idea. But warming has consequences, and there are some consequences that scientists understand really well. So, as most of us have experienced this boreal summer, climate change means hotter heat waves. Scientists know that climate change makes heat waves hotter, longer, and more frequent. So why is this? So first of all, there's a very simple kind of thermodynamic argument. It's hotter on average, so we would also expect more extreme heat waves too. But there's also compelling arguments for a dynamical shift. Humans are messing with the circulation of air through the atmosphere. So we know that the Arctic is warming faster than anywhere of air through the Earth's atmosphere is driven by the temperature contrast between the hot tropics and the cold poles. And that temperature contrast is getting less and less and less as the poles heat up more and more and more. So there's reason to expect that that is messing with the atmospheric circulation. It's making the jet stream more unstable, and it's favoring the conditions that can sort of trap heat domes and keep them around for a really long time. That's something that we saw this summer in Phoenix, Arizona, which was above 110 degrees high temperature for, I think, 31 consecutive days. But there is another thing going on as well. Land is just like people in that it sweats in the heat. So when you get really hot, your body covers you with liquid. You sweat. And that is because when it takes energy in order to turn a liquid into a gas. So sweating and allowing that liquid water to evaporate away from your skin transfers heat away from your body, cooling you down. The land surface is very similar. So when it gets hot, water is evaporated away from the land surface. So as the Earth gets hotter, more and more and more water gets evaporated from the surface and it gets drier. So very, very dry ground, completely parched. It can't cool itself off by evaporation because there's no more water left. And so that very efficient way of cooling itself is now taken away and it gets even hotter. So this is an example of a feedback process that we call the soil moisture feedback. So climate change also means higher drought risk. And that's because, as I mentioned, warmer air is thirstier air. So even if there are no large-scale changes in rainfall patterns, and that is a big if, increased evaporation alone can dry out the surface, sucking that moisture away and leading to soil moisture or agricultural drought. But all of that evaporated water doesn't just disappear. It has to go somewhere. And that is why we expect that climate change will lead to more heavy precipitation. So in general, there is more rainfall on average in a warmer world because more moisture is being evaporated away from the surface. But there is a lot of evidence that extreme rainfall, very, very heavy downpours, those are actually rising faster than average rainfall. And this is because warm air holds more water vapor, about 7% more per degree Celsius of warming, or 1 degree Fahrenheit, or 4% for every degree Fahrenheit of warming. And what this means is that when it rains, it pours because there is simply more water around to dump on us. Climate change also means sea levels rise. And this is happening for two main reasons. So first, water right now is locked up on land inside of ice sheets or mountain glaciers. And when it gets hot, ice melts. So that water that used to be parked on the land is now running into the ocean. But there's something else going on too. Ocean waters are getting warmer and warm water expands. Now, both of these things are contributing to sea level rise right now. We also have evidence that climate change makes hurricanes not necessarily more frequent, but certainly stronger, and it makes their impacts more severe. We know that warm water is hurricane food, and we know that rising sea surface temperatures fuel stronger storms. And these storms mean different things now. So in 2017, Hurricane Harvey hit Houston, and Houston experienced the fact that now rising temperatures mean heavier rainfall because warm air holds more water vapor, and the Hurricane Harvey had more water vapor to dump on Houston. And as sea levels rise, the dangerous surges from these storms can also now reach farther and farther and farther inland. Now, fires are very complex. They depend on things like fuel availability, ignition, whether that's lightning or humans, and suppression. But we know that fire weather, the kind of hot and dry conditions that make fires more likely and more dangerous, we know that that is increasing in many places due to climate change. So to recap, we know a lot about why climate change is happening and what it means. We know the world is warming, we know why, and we know what this means. We know there are known consequences of warming: more heat waves, more downpours, higher sea levels, stronger hurricanes with higher storm surges that can dump more water on us. But we don't know everything. Now, I want to be really, really clear. We don't know everything. We don't know nothing. There are some things that we know very, very well. But I want to talk a little bit about the uncertainty here, because that's my job. As a scientist, it's my job to think about the things we don't know and think about ways that we could know them. So I want to pivot here and talk a little bit about the many, many things that we still don't know. We don't know something very, very basic. We don't know how hot it's going to get. And when I tell people that, they're like, come on, scientists, you guys had one job. But we don't know how hot it's going to get for many different reasons. The future scenarios used by the climate modeling community, those project by the end of the century anywhere from about 1.5 degrees of warming Celsius to almost 5 degrees Celsius, or more than 5 degrees Celsius of warming. So for reference, remember 5 degrees Celsius was roughly the difference between now and the last ice age. So there are several reasons we can't tell you exactly what to expect by the end of the century. So the first is we don't know how the Earth responds over the long term to elevated levels of carbon dioxide in the atmosphere. We don't know how hot it will get because we don't know how the Earth responds. And that is simply because we have never done this experiment before. We've never kicked the Earth system this hard. And we do know that temperature changes change things about the Earth. Temperature changes lead to climate changes in clouds, in rainfall, in vegetation. And these climate changes can themselves feed back and affect the temperature changes. So for me, the most intuitive feedback is what we call the ice albedo feedback. Remember albedo, kind of shininess? Well, ice is extremely shiny and very reflective. So if you have a lot of ice around, that is turning back a lot of sunlight that would otherwise reach the Earth's surface and warm it. Now, as it gets hotter, the ice melts, and that reveals darker ocean or ground below, and that's more absorbent. And so we expect that there will be an ice albedo feedback, and there is already an ice albedo feedback as the Earth warms up. And this is something that makes the warming worse. But we know about ice. Scientists understand that ice tends to melt when it gets warm. What we don't understand, at least not completely, is what clouds are going to do. Any changes to clouds, their location, their opacity, their height, how many of them there are, affects how much sunlight they can block, and it affects how much heat from the Earth's surface they can trap. So this makes clouds the wild card. One of the reasons we don't know exactly how hot it's going to get is we don't know what clouds are going to do. We do know for sure that clouds are not going to organize themselves to save us from warming. They're not going to be a substantial stabilizing feedback to climate change. And our best guess is that if we double carbon dioxide in the atmosphere, the Earth would warm around 3 degrees Celsius. That's what we call the climate sensitivity to doubled carbon dioxide. But there's still a lot of uncertainty there. There's another scientific uncertainty here. We don't know how much carbon dioxide is going to stay in the atmosphere because we don't know how the carbon cycle responds. What do I mean by this? Well, right now, humans are emitting greenhouse gases, carbon dioxide, but also methane, nitrous oxide, F gases, and these come from a variety of sectors. And the biosphere, things that photosynthesize, forests, grasslands, phytoplankton in the ocean, kelp, that's responding. Humans have put greenhouse gases in the atmosphere, and the biosphere has responded by taking up more of the carbon dioxide that we emit. But there is no guarantee that the biosphere is going to continue to do this in the future. We could see wildfires or desertification, and this would reduce the amount of carbon that plants on land can take up. It is really difficult to take up carbon dioxide from the atmosphere when you are on fire. We don't know what's going to happen to phytoplankton in a changing climate. And the things we do know are really scary. We know that when it gets warmer, permafrost thaws, and this releases methane and especially carbon dioxide into the atmosphere. Now, these are called carbon cycle feedbacks, how the ability of the biosphere to take up carbon in the atmosphere changes as carbon dioxide concentrations increase. These feedbacks are really, really uncertain, especially as emissions increase. But the scariest thing about the future is we can't predict exactly when we might exceed what's called tipping points in the climate system. So what do I mean by tipping point? Well, a tipping point is essentially a point of no return, at least not within timescales relevant to human lives or civilizations. It's a change in some aspect of the Earth system that we can't fix in a lifetime. So an example of a tipping point would be the disintegration of the Greenland or West Antarctic ice sheets, shifts or die-offs in the Amazon rainforest or the boreal forests in the Northern Hemisphere, and circulation changes like a shutdown of the thermohaline circulation or the deep ocean conveyor belt. And the thing is, we don't know exactly when any of these changes might be set off. We only know that the risk increases with warming. So we are not safe, even if we manage to stay below the 1.5 degrees Celsius target. But conversely, we're not doomed if we exceed the 2 degrees Celsius target or any other target. Nature does not think in degrees Celsius. These targets are just that. They're targets that we have set for ourselves. I think the UN is right when their messaging says every 1/10 of a degree matters, every ton of greenhouse gas that we don't emit matters. And that brings us to the largest source of uncertainty. We don't know how hot it will get because we don't know what human beings are going to do. So remember this graph and its really confusing labels? These labels correspond to different possible future scenarios. Remember I said climate models run on stories? These are different stories about the future that we could tell. So let's do a rough translation of these labels here. This red scenario up here corresponds to a future of heavy fossil fuel use and no climate policy and very, very high emissions. The blue scenarios down here correspond to futures of sustainable development and strong or very, very strong climate policy. So how hot is it going to get? I mean, yes, there is a lot of uncertainty in the science. There's a lot of things that we don't understand about this rapidly changing planet. But ultimately, the answer to this question is up to us. How hot will it get? We can choose. I don't like that story. I don't like the red story that I showed you, the future of no emissions cuts and really dangerous warming. But right now, that's just the first draft of a future. And as Cynthia mentioned, I am writing a book right now, and I can tell you the first draft of anything is really bad. You have to edit it. You have to change it. And I think we can change it. So you may have heard that the future is not in our hands, that we should give up because we have already doomed ourselves to substantial warming in the pipeline. But this isn't true. This is a misconception. When we stop emitting greenhouse gases, the science says that the warming will stop. So substantial future warming is not inevitable. So why is this? Well, there's two competing processes at work here. First, we need to understand a little bit about the ocean's role in the climate system. So the vast majority of the heat that human beings have added to the climate system has gone into the ocean. We are adding about 5 nuclear bombs worth of energy to the ocean every second. So if the ocean weren't there, we wouldn't be 1.2 degrees Celsius warmer. We would be 30 or 40 degrees Celsius warmer. And when we reach net zero, the rate at which the ocean takes up heat will begin to slow as the whole system starts adjusting to a new equilibrium. and this will have a warming effect. So if atmospheric carbon dioxide concentrations remained constant, this would mean much more warming in the pipeline. But once we stop adding greenhouse gases to the atmosphere, something else is going to happen. The things on the land and the ocean that photosynthesize, the biosphere, will start taking carbon dioxide out of the atmosphere, as they are currently doing. And at net zero, we will not be putting it back. So atmospheric carbon dioxide levels will start to decline. And these two things roughly cancel each other out. Our best estimate as scientists of the warming in the pipeline, it's 0. The science right now says that when we reach net zero, the warming will stop. So what do I mean by net zero? Well, net zero, from a climate modeling and scientific perspective, is the point in time when any residual greenhouse gas emissions are balanced out by carbon removal. So to understand what I mean by net zero here, we have to understand what we mean by greenhouse gases. So human activities emit not just carbon dioxide, but multiple greenhouse gases. So over long timescales, the breakdown of greenhouse gases emitted by humans looks something like this. So carbon dioxide dominates, but there are also substantial contributions from methane, nitrous oxide, and F gases. So the most prominent greenhouse gas is carbon dioxide. And the thing to know about CO2 is that the CO2 that is not removed by the biosphere stays in the atmosphere for a really long time, centuries or even thousands of years. And what this means is that the cumulative emissions of carbon dioxide matter. Some of the carbon dioxide emitted at the beginning of the Industrial Revolution is still there in the atmosphere, still causing warming today. So today's emissions are adding to an enormous pile that are already there. But carbon dioxide is not the only greenhouse gas emitted by human activities. Methane is also a pretty powerful planet warming gas. Methane is emitted by agricultural activities, cow burps, flooded rice fields. It's also emitted by the fossil fuel industry. Natural gas, I'll put it in scare quotes here, is methane. And leaks from wells and pipelines are really large sources of methane emissions. As stuff rots in landfills, it also is a pretty substantial source of methane. And the thing to know about methane is that it is potent. It's about 80 times more powerful than carbon dioxide. But unlike carbon dioxide, methane does not linger around in the atmosphere for a really long time. Methane is naturally removed from the atmosphere by chemical reactions in about 12 years or so. So methane, super potent, relatively short-lived. Nitrous oxide is a small but important contributor to warming. It's about 4.5% of our emissions. And its main source is nitrogen fertilizer application. The bad news is that nitrous oxide is even more potent than carbon dioxide and even more potent than methane. And the worst news is that it stays in the atmosphere for over a century. Finally, F gases. F gases are synthetic or human-made gases that are often used in coolants and propellers in AC units and refrigerators. And the most potent F gases were banned by the Kigali Amendment to the Montreal Protocol, which is the protocol that essentially fixed the ozone layer. And the really good news is that this amendment was actually ratified by a bipartisan majority in the US Senate last year. So some of these emissions, particularly agricultural methane emissions and some industrial sources of CO2, are relatively hard to abate. We don't know how to zero them out yet. So we would need to cancel them out by removing carbon from the atmosphere. So practically, in most scenarios, net zero actually means carbon negative. So this means that carbon removal is a part of the solution. But carbon removal can only be a very, very small part of the solution. So why small? So let's look at how we would actually practically remove carbon dioxide from the air. So the good news is that nature knows perfectly well how to remove CO2 from the atmosphere. Plants and phytoplankton remove CO2 from the air through photosynthesis, which I believe is pretty much magic. Some ecosystems are really, really good at this, really effective at storing carbon. Coastal mangroves, seagrass meadows, tropical rainforests. And there's certain agricultural practices that can enhance the ability of the soil in which these plants grow to capture and store carbon. But trees don't exist to fix human mistakes. Trees exist to exist. And when they are done existing, when they're done with life, they are done storing carbon. Trees also take up land. So to offset the emissions from just the United States, we would need a forest the size of Texas. And there's limits to how much carbon can be stored in the soil. So I want to be really clear here. I'm not anti-tree. I love trees. We should protect the trees that exist. We should plant more, but we cannot plant our way out of climate change without emissions reductions. So what about engineered solutions? Because after all, humans know how to remove carbon dioxide from the air. NASA has had to think about CO2 removal for years because you cannot lock a bunch of astronauts into a tiny module and shoot it into outer space and not think about how to filter out the carbon dioxide that they're exhaling. So this is actually a major plot point in the movie Apollo 13, which turns out really holds up after all these years. I totally recommend it. But you can use relatively similar technology to suck carbon dioxide out of the air. And people are doing this. This process is called direct air capture. But carbon dioxide is much, much, much more diffuse in the atmosphere than it is in a tiny, cramped spacecraft with 3 guys inside it. So you need a lot of energy to capture it. People are also looking to speed up the geological carbon cycle by enhancing rock weathering and trying to figure out ways to force the ocean to take up more carbon dioxide. You can shock it, you can dump antacid into the ocean, and all of these things to varying degrees are promising technologies. They are really cool science. I'm excited by some of these things, but I think a little perspective is in order. The largest direct air capture plant that's currently in development might eventually, if we are very lucky, be able to capture 1 million tons of carbon dioxide. That sounds like a lot. 1 million tons. That's great. But for reference, global CO2 emissions in 2022 were 40.5 billion tons. So what this means is that this proposed plant, which is not even operational yet, will use an enormous amount of energy and resources to remove 0.0025% of global emissions. And it's those cumulative CO2 emissions that matter for warming. So if you add up all of the CO2 that humans have put in the atmosphere, you will find that it weighs over 1.5 trillion tons. The CO2 that humans have put in the atmosphere weighs 25,000 times more than every human being on Earth put together. It weighs more than 3 times as much as all life on Earth put together. So yes, it is worth pursuing these technologies. Yes, we will need some carbon removal to balance out emissions from hard to abate sectors. But removal is not going to be able to enable the status quo of high emissions. It is not going to save us from ourselves. So there's one more thing that we could do to hack the planet. We know that when certain types of volcanoes erupt, they block the sun, they cool down the earth. So what if we didn't wait for a volcano? What if we were the volcano? And so there are different ways to mimic a volcano. We could just shoot gas and dust and soot into the atmosphere like volcanoes do. We could make high cirrus clouds thinner, which would allow more heat from the planet to escape to space. We could brighten low, thick clouds over the ocean to block sunlight that way. And the thing is, we're pretty sure that all of these methods would work for some definition of work. We're pretty sure that these would lower the temperature of the planet because when you block the sun, it would get colder. But they would do this not by cutting emissions, but by blocking the sun. And it turns out that a lot of things on Earth like the sun, plants, the water cycle, solar heating drives the winds, it drives the water cycle. And we have reason to believe that certain stratospheric aerosol injection techniques would damage the ozone layer. And if we scattered too much sunlight, we would turn the sky from blue to white. And the scariest thing is that aerosols don't hang around for very long. So if we decided to do this, to block the sun, we would need to commit to doing it indefinitely. And if we stopped, we would risk what's called termination shock, where we would get years worth of global warming in a few months. And this would be an incredibly dangerous outcome. So blocking the sun, risky maneuver. To limit warming, we really need to achieve net zero. And it is not possible to achieve net zero without cutting emissions really dramatically. And the longer we wait, the more drastic these cuts would have to be in order to achieve our goals. So if we had started making cuts 20 years ago, we would not have such a hard road ahead. In 2020, when the pandemic shut down most industries, almost all travel, all of those shutdowns led to emissions falling by 7%. To limit warming to 1.5 degrees Celsius, we have to cut that much every single year. But there is good news. The good news is we know exactly how to do this. We know where the emissions are coming from, and we have the solutions that we need. So those of us here at Project Drawdown are working on researching these solutions, implementing them, evaluating them. But there's bad news. The bad news is that even if we do everything right, it's going to take a very, very long time before we see action paying off in the climate. So even if we reach net zero by the middle of the century and limit warming to 1.5 degrees Celsius, the climate is going to look relatively similar to the worst case scenario for at least the next few decades. But it is more than worth it for the future that our children and grandchildren will live in, because the world in 2100 looks very, very different in an emission cut scenario and in a no emission cut scenario. So yeah, I want a better life for my children, fine, but I also want a better life for me. And the thing to note is that fossil fuel burning emits both greenhouse gases and aerosols, as I talked about at the beginning of the talk. And aerosols have that cooling effect on the climate, but they don't just have an effect on the climate. They pollute our air and they affect us. So worldwide, more than 11% of deaths are attributed to air pollution. This is something that is killing millions and millions of us. And a recent paper published estimated that getting rid of fossil fuels will save between 3 and 4 million lives every year. When you cut out fossil fuels, that air pollution goes away. It goes away immediately. And so these are benefits that do not just accrue to our children and grandchildren. We start experiencing the benefits of cleaner air immediately. And that's not all. If you support carbon dioxide sinks in forests and the ocean, this can also help us protect the biodiversity and the ecosystems that we love and that we depend on. And climate solutions have many benefits, most of which won't just come to our children and grandchildren, most of which we will experience in our lifetimes. So what does a climate model show you about the future? That depends on the story that you tell it. A climate model is very, very literally a world-building machine. It shows you the worlds that were, it explains the world that is, and it tells you the worlds that could be. So many of the stories that we all grew up with follow the same basic structure of the hero's journey. There's a leap into the unknown, there's trials and tribulations, there's a really low point, and there is a triumphant return. And this is a really satisfying story structure. It's satisfying because the characters don't just give up when stuff gets hard. And these stories exist in the first place because the characters decide to go. So wherever you are on your climate journey, I am so grateful that you have started. I am so glad that you're here. I'm really, really happy that you have decided to cross that threshold. So there is so much that we can do. Let's get to work. Thank you so much. Really happy to take questions.
Super. Thank you so much, Kate. Well, I've got a long list, so we'll see what we can get through. First one that's received lots of votes is what are some of the actions or solutions you're seeing that give you the greatest sense of optimism?
So I can answer that question on multiple levels because I'm actually optimistic on multiple levels. But to explain why I'm optimistic, I want to go back to 2018 when I was not optimistic, when I was really, really pessimistic, very, very cranky. The UN that year was putting out a report on the world at 1.5 degrees Celsius. And I was like, this is so useless. Like, this is fan fiction. We're not going to do this. Why do we care what the world at 1.5 is going to look like? We're just not going to do it. And also, like, why do we need another climate report? We have had so many IPCC reports. We have so many national climate assessments. Oh, great. Yeah, let's write another report and everybody will listen to this one. And I was so wrong because something about that report and the media coverage really, really, really touched a nerve. So Greta had begun her school strike for climate earlier that year before the report came out. And something about the report coming out and the coverage triggered millions of people to join her. So you really started seeing the emergence of this mass movement of Sunrise Movement, Extinction Rebellion, larger climate movements, people really starting to stand up and take that seriously. And as somebody who's very used to being ignored, that was very weird. That was very weird seeing people finally take climate change seriously. So that is something that I'm really excited about. The fact that in 2016, there was not a single question asked at the presidential debate about climate, not a single one. And in 2020, that would have been unthinkable. The Democrats had an entire town hall on climate, which was honestly very boring, but at least they had it. So the fact that people are starting to take this seriously, I think is really exciting to me. I am excited about solutions in every sector. So if you look at where emissions are coming from, they're coming from the power sector. Very excited about the advent of renewables and battery technology there. They're coming from the transportation sector. I'm excited about EVs, but I am even more excited about movements to build denser, more walkable cities and reduce the need for individual car transportation. If you look in the building sector, people who know me can confirm this. My only personality trait is person who owns an induction stove. I invite people over and make them watch me boil water. It's incredible. But I'm really excited about building electrification. I think that's great. When it comes to the agricultural sector, I think there are a lot of climate smart agricultural practices that are starting to catch on, things like no-till agriculture. I also think there's a growing awareness that, hey, a third of the stuff that gets farmed never gets eaten. So let's think about ways to minimize food waste. And in the industrial sector, making stuff, I'm really excited by sort of new scientific developments to try to make steel using hydrogen, to try to make concrete in different, lower emission ways, to try to make alternatives to plastics. So I think, no matter which sector you look at, there's really exciting things happening. Maybe not as fast as we want them to, but that's why you guys are here, honestly, to help, to be the accelerant there.
Exactly. Thank you, Kate. Kind of related to that, is there anything going on with the oceans that is exciting to you? So the question is, can you talk more about the ocean's role? So much is going into decarbonizing and electrifying. Are there any priorities like this for the oceans?
Yeah, so I'm a big ocean fan, love the oceans, have a little 3-year-old who watches the Octonauts obsessively and knows more about ocean ecosystems than I ever will. The more we study about oceans, the more kind of grateful we are for what they do for us. I mentioned taking up all the heat, taking up the carbon. I'm also, we're also kind of realizing, hey, these coastal ecosystems, these seagrass meadows, these kelp forests, these mangroves wow, those things are taking up a lot of carbon. Not only do they take up carbon, but a lot of them are actually really good buffers against storm surges. So I'm really excited about coastal ecosystem restoration work. In New York, we've got the Billion Oyster Project, where they're putting back the oysters that basically everybody ate. Oysters are really great at filtering pollution out of the water, and having those reefs there is a really useful adaptation measure because it is a buffer against storm surges coming in. I'm a little bit I'm interested in the science of marine carbon dioxide removal. I agree with most of my colleagues, ocean scientists working in trying to understand marine carbon dioxide removal, that it might work. It's interesting science, but we should assume and proceed as though it is not going to work. We shouldn't count on the oceans to be able to take up more carbon dioxide than they already are. But that said, there are people working really hard on figuring out, well, the oceans are acidifying right now. What if we just basically dump a bunch of antacid into the ocean? Would that reverse ocean acidification and have the side benefit of making the oceans take up more carbon? Nobody knows right now. Nobody knows the side effects. Nobody knows the consequences of that. That is a useful thing to study in a very responsible manner. But I think everybody working on it would agree with me that we should assume it's not going to work.
Gotcha. And would you say that ocean pollution would inhibit the ocean's ability to absorb heat if we continue our current waste practices?
Yeah, I mean, so things in the ocean are contributing to a thriving ecosystem. And we know that diverse ecosystems do a great job of taking carbon from the atmosphere. So please, nobody go and post on Twitter or whatever it's called now that Kate Marvel said whales are going to save us from the climate. Whales are not by themselves a climate solution, but whales are big carbon-based life forms. They are made of a lot of carbon. And when whales are done with life, they sink down to the ocean floor and they sequester carbon. So the more carbon goes into living things in the ocean, the better. And things that we do to the ocean that inhibit the ability of those things to live and thrive is affecting the ability of the ocean to sequester carbon. So it's it depends on what perspective you look at it, but the story is the same either way. If you care about carbon sequestration, you want thriving ecosystems. If you care about thriving ecosystems, you want to reduce the greenhouse gases in the atmosphere.
Great, thank you. How does the scientific community think about how we'll know if and or when we've hit the tipping point? Is this something that can only be done in retrospect?
Unfortunately, yes. We cannot say, well, we can warm exactly this much, and if we go any over that, we are going to hit a tipping point. There is not that certainty in the science. And I think that is one of the scariest things. If we were certain, this is when this tipping point is going to be breached, or this is when your community is going to be flooded, or this is when the seas are going to rise and make it impossible to live in this particular city, we could take steps accordingly using that certainty. But we don't and are never going to have that certainty. The reason we're not going to have that certainty is the Earth is an incredibly interconnected place. There are many different things that live and exist on the Earth's surface. We've got air, we've got water, we've got ice, we've got land, we've got things that live on the land, we've got things that live on the land and make decisions and burn fossil fuels. So it's all extremely complex and intertwined. And that makes it really, really difficult to say, this is the threshold when this tipping point will be reached. We do have evidence that things like the Atlantic meridional overturning circulation, so a really important component of the thermohaline circulation, that is slowing down, that is shoaling. And we know that that is happening because we're getting less sea ice formation and less water sinking down to the bottom and flowing around that. Now, I've seen some extremely terrible news coverage that are like, the Gulf Stream is going to shut down. Gulf Stream is not going to shut down. As long as the Earth is round and turning, there will still be a Gulf Stream because that's a surface current driven by the wind. But it is not a great idea to shut down the long-term thermohaline circulation. But if that happens, we are not going to get a day after tomorrow type scenario. We're probably going to see shifts in precipitation patterns, which themselves will be really, really, really difficult to anticipate and deal with. But I kind of feel like we have enough to worry about without worrying that, Dennis Quaid is going to freeze the world or whatever happens in that movie.
Gotcha. Thank you. Given the nature of your work, you deal with stuff that's really hard to deal with emotionally, probably on a daily basis. How do you keep going? What motivates you?
So I feel many things. I don't think there's only one way to feel about climate change. So sometimes I feel very scared. Sometimes, a lot of the time, I feel very angry. I feel very sad. But I also feel kind of a deep sense of gratitude. I feel a deep sense of joy in being part of a community of people who are working on climate solutions and understanding what's happening. Because once you kind of make the leap into the climate field, you kind of realize like, oh my God, like the best people in the world are here. Like all these people are incredible. And I really love being part of that community, although like the imposter syndrome is something else to talk about. But, I also feel like it is just incredible that we can understand this stuff. Like it is incredible that we have the science we need in order to really understand what's going on. And so I always make sure to sort of cultivate that sense of wonder as well. As Cynthia mentioned, I'm writing a book, and the book is looking at climate science through the prism of 9 different emotions. So the first chapter is wonder, and then there's grief and anger and fear and pride, and then ending up with hope and love. And so, I feel all of those things on any given day. And I think there's no one way that one should feel about climate change.
Well put. Thank you, Kate. I think I'll try and sneak one more here in the 2 minutes that we have remaining. So uncertainty means different things in science and real life. How do you deal with the ambiguity this creates?
I think it's really important to not try to impose false certainty on it. I think I'm not a psychologist, I'm not a social scientist at all, but it's my understanding that there's a lot of research out there and also a lot of anecdotal evidence that human beings are terrible at ambiguity. We are terrible with uncertainty. It drives me crazy personally. It's really, really difficult to handle. But I think you have to be very careful not to say, well, I can't deal with the uncertainty, so I'm going to impose a false certainty onto it. And I think that's what you see happening a lot with people saying, we should give up, we're all doomed. Particularly, some novelists who like to publish things in the New Yorker, have this messaging that, we should all give up. We should all just sit in, I guess maybe we could all go to Jonathan Franzen's house and sit in his garden and like wait for the apocalypse. But I think that is an attempt to impose a false certainty on something that is fundamentally very, very, very ambiguous. We don't know what's going to happen. We don't know exactly what the feedbacks are going to be. We don't know what the carbon cycle is going to do. We don't know when a tipping point is going to be breached. And we don't know what humans are going to do. We have control over several of those things. Like if we can control what humans do, if we can make the choice to bend that emissions curve, then maybe we don't find out. We don't do those other experiments. I would be perfectly happy as somebody who has spent, 12 years studying how sensitive the climate is to doubled carbon dioxide. I would be really happy never finding that out. So I hope that we do not do that experiment.
Excellent. Thank you so much. Ashwin, I'll turn it over to you.
Thank you, Alexis, and thank you, Kate. This is great. And I mean, thank you firstly for all of your work. It's clearly showing us a path of what is necessary and also what is possible. And also coming today to speak with our community and explaining so many really complex concepts to us in such elegant language. Something that I'm going to think about a lot and that's going to stay with me is climate models are fueled by stories. They run on stories. So that was a really great one. Also, the audience, thank you for being here today and for amazing questions. I could see a lot of engagement on the chat. That was great. If you haven't already, please do check out our Learning for Action course on our website, terra.do. Thanks for coming and hope to see you at more events like this one. Thank you all.
Take care, everyone.